Imagine you're reading a story and you come across the sentence, "I deposited cash in the bank." Now compare that to, "The children played near the muddy riverbank." Same exact spelling, but a completely different meaning. As humans, we don't even pause to figure this out. Our brains automatically use the surrounding words to know which version of bank we're dealing with. But for early artificial intelligence, this was a massive roadblock. Machines couldn't tell these meanings apart, causing them to fail at basic reading comprehension. To understand why, we have to look at how older language models, like Word2Vec, worked. They translated text into lists of numbers called vectors, which act like mathematical coordinates for meaning. The problem was that they used what is known as a static embedding. Think of this like a permanent ID card assigned to every word, and that ID card never changed. Because the machine only had one ID card for bank, it blended conflicting meanings, like financial loans and muddy water, into a single confused representation. These systems treated language like a rigid dictionary, ignoring how the words around a sentence actually dictate what a word is supposed to be. This changed with a breakthrough called ELMo, which stands for Embeddings from Language Models. ELMo solved the fixed meaning problem. Instead of relying on a static ID card, ELMo creates a contextual embedding. This means it generates a brand new, customized set of numbers for a word based entirely on the specific sentence it lives in. Think of a word like an actor. The same actor plays different roles depending entirely on the other character words sharing the stage with him. When ELMo sees the word bank surrounded by words like loan and credit, it puts on a finance identity. But surrounded by river and muddy, it assumes a geography identity. Resume normal pace. This shifted the focus of AI. It stopped looking at words in isolation and started analyzing the ecosystem of the entire sentence. To figure out that ecosystem, ELMo uses what's called a bidirectional language model. Bidirectional simply means it reads in two directions at once. First, ELMo reads forward, from left to right, to see the words that come before the target word. Simultaneously, it reads backward, from right to left, to see the words that follow. By scanning from both sides, ELMo ensures that a word like not properly flips the mathematical representation of good from a positive sentiment to a negative one. ELMo also goes deeper than the sentence. It looks inside the spelling of the word itself, using what's called character-level representation. Notice how the word playing breaks apart here. By analyzing the letters, the AI recognizes shared roots, connecting playing with played or player. This prevents the AI from failing when it encounters rare vocabulary or new word forms it hasn't seen before. These context-aware vectors immediately upgraded the systems computers use to understand our language. It improved the AI's ability to label parts of speech, enabling it to distinguish the physical book you read from the action to book a flight. It also improved how machines identify specific names like people or companies, a task called named entity recognition. Now the machine knows Apple, the fruit, is different from Apple, the tech company. By removing this confusion, ELMo allowed AI to make accurate decisions based on what a person actually means, rather than just the words they used. While revolutionary, ELMo used an older memory system that processed text one word at a time. This was slow and sometimes struggled to connect ideas across very long paragraphs. That paved the way for newer systems like BERT, which use attention to look at every word in a sentence simultaneously. ELMo was the crucial bridge that moved the industry from simple dictionary lookups to understanding sentences as a whole. It was the first major milestone to prove that a machine must read the whole sentence before.
Welcome! Today's explainer is all about demystifying a truly revolutionary piece of technology. You know, for decades, computers were just counting words, literally treating them like isolated math problems. But today, we're going to explore the exact architecture that taught machines how to actually understand them, mapping context just like you and I do. Let's get right into it. Here is our structural roadmap for today. We'll start with the problem of context, enter BERT, the magic of attention, how BERT learns, putting BERT to work, and finally, we'll wrap up with its legacy and limitations. Section 1, the problem of context. Human language is incredibly messy, inherently ambiguous, and heavily reliant on what surrounds a word. So let's start with a relatable little puzzle. Think about the word bank. To a human, it's instantly obvious what this word means depending on the sentence it lives in. But to a machine, well, B-A-N-K is just a string of characters. How on earth does a computer know if you're talking about depositing a check or sitting by the water? And this brilliantly illustrates our core problem. Take these two sentences. The bank approved my loan versus the riverbank was muddy. Older natural language processing models like Word2Vec or Glove usually assigned one single fixed mathematical vector to the word bank. So they effectively blended a financial institution and the edge of a river into one incredibly confusing concept. They treated words like static dictionary entries, not like dynamic actors whose roles completely change depending on the scene. Looking back, we can actually see how this builds historically. In the 1950s, we had bag of words, which literally just counted words as if they were items dumped in a bag, ignoring grammar entirely. By the 70s, TF-IDF helped weigh the importance of certain words. Then in 2013, Word2Vec gave a static similarity, so it knew king and queen were related, but it still gave each word one fixed meaning. By 2018, a model called ELMo finally introduced contextual reading, but it read sequentially, step by step from left to right. And then, later that same year, everything changed. Section 2. Enter BERT, the context revolution. This is the architecture that fundamentally rewired how we build natural language processing systems. Okay, let's break down this heavy acronym. BERT stands for Bidirectional Encoder Representations from Transformers. I know, it sounds super intimidating, but the core idea is remarkably elegant. It's a transformer-based model that reads a sentence from both sides at the exact same time. Instead of reading left to right like a human reading a book, BERT looks at the entire sentence at once to create a deep, mathematical understanding of what every single word is doing in that exact, specific context. So, instead of acting like a static dictionary, think of BERT like a detective. Before deciding what a word means, it hunts for clues by forcing that word to look at every other word in the sentence. It lets the surrounding context define the word rather than the word defining itself. Section 3, the magic of attention. Words talking to words. Let's look at the specific mathematical mechanism that makes this deep, web-like reading possible. Take a simple three-word phrase, not good. A weak, older model might spot the word good, count it, and predict that this sentence has a positive sentiment. It completely misses the structure. But BERT uses something called self-attention. Self-attention allows the word good to look directly backward at the word not. The model sees that not modifies good, allowing it to instantly flip the sentiment and understand the overall negative meaning of the scene. It's a total game changer. And BERT doesn't just do this once. It has multiple attention heads. You can think of them as a classroom of highly specialized students all discussing the sentence together. One attention head is the grammarian, finding subject-object links. Another is the critic, linking emotions to nouns. Another is the contrarian, looking for negation. And another is the detective, figuring out exactly which noun a pronoun like it refers to. They process all these relationships simultaneously, turning a linear sentence into a rich, interconnected web of meaning. Section 4. How BERT learns. Filling in the blanks. If that is how it reads, how do we actually teach a machine to do that? Well, to teach BERT to be such a careful reader, researchers used a brilliant technique called masked language modeling. Imagine a student taking a fill-in-the-blank test. During training, researchers literally masked certain words in massive amounts of text and forced the model to guess what was missing. For example, the student opened the blank and started reading. To solve this puzzle, BERT has to rely on bidirectional deduction. It looks at the left context. The student opened the, which suggests an object. Then it looks at the right context and started reading, which suggests a text. Together, those clues from both sides point directly to the word book. Older models that only read left to right could only guess based on the past. BERT uses the past and the future of the sentence to deduce the present. Section 5, putting BERT to work, from learning to doing. Now that we have a highly trained, context-aware machine, how do we connect this architecture back to the real world? First off, we need to clear up a massive point of confusion in the AI space, the difference between BERT and GPT. BERT is an encoder-only model. It's the careful reader. Its job is to deeply understand and map the input text you give it. GPT, on the other hand, is a decoder-only model. It's the excellent writer. Its architecture is built to predict and generate brand new text output. Basically, you use BERT when you need to understand something deeply, and you use GPT when you need to write something new. In the real world, developers use a highly efficient pipeline. Step 1 is pre-training, where BERT reads massive amounts of text to learn general grammar and facts. Step 2 is fine-tuning. Instead of building a completely new model from scratch for every single task, developers take this pre-trained BERT brain and train it just a little bit more on a specific labeled dataset. Finally, in step 3, this fine-tuned model is deployed to perform specific applications, like analyzing the sentiment of movie reviews, identifying names and locations in legal documents, or even powering the search ranking algorithms you use every single day. Section 6, Legacy and Limitations. Taking an impartial look, it's important to see where this architecture falls short and what evolved from it. We definitely must note that BERT is not perfect. It's computationally very heavy and requires massive memory compared to older models. It also has a strict 512 token input limit, meaning you can't just feed it a whole book at once. You literally have to chop the text into chunks. And, as we established, it's not designed for open-ended text generation. For simple, keyword-heavy tasks, older models might actually be a faster, cheaper choice. It's also worth pointing out that, like many models, it can inherit social and linguistic biases directly from its training data. However, BERT's true legacy is that it acted as a bridge to modern AI. It proved absolutely that attention-based bidirectional understanding works. And it spawned an entire family tree of descendants. RoBERTa optimized the training process. DistalBERT made the model smaller and faster for production. ALBERT made it highly parameter efficient. SentenceBERT optimized it specifically for semantic search. And domain-specific versions like FinBERT for finance and BioBERT for medicine proved that you could teach this careful reader the specific jargon of literally any industry. Which leaves us with this final thought. BERT shifted machines from merely counting our words to mapping the intricate webs of relationships between them. It taught computers that context is everything. So if machines can now map these relationships as well as we do, how will that change the way they interpret everything we write in the future?
Welcome to The Explainer. Today we're going to explore a really monumental shift in artificial intelligence. We're looking at exactly how computers finally learned to understand the true underlying meaning of human language. It is a completely fascinating journey, taking us from simply counting words all the way to actually mapping human thought.
Okay, let's dive right into this. Think about this question for a second. How does a machine know that king and queen are related? Now, to you and me, the connection is instantaneous, right? But a computer? Well, a computer doesn't naturally understand words at all. It only understands numbers. So when it looks at the actual letters in king and queen, it is completely blind to the obvious human connection between them.
We inherently just know these pairs belong together. We know doctor belongs near hospital, and that happy and joyful basically express the exact same emotion, but these words are connected by meaning, not by numbers. And this established a massive challenge for early AI researchers. I mean, how do you teach a strictly math-driven machine to see these exact same semantic relationships?
Let's start with section 1, the failed attempts, counting versus understanding.
To really appreciate the solution, we first need to look at history. Before we could map meaning, we went through 3 main eras of trying to represent words. Era 1 was one-hot encoding. This method gave every single word a unique position, kind of like a student's roll number. It gave the word identity, sure, but to the machine, king and queen were just as different as king and apple. Then came Era 2, bag of words. This simply counted how many times words appeared. Think of the ingredient cluster analogy here. Bag of words is like counting ingredients, pasta, cheese, tomato, without actually understanding that they belong together in Italian cuisine. It gave us frequency, but literally no meaning. Finally, Era 3 was TF-IDF, which weighed the importance of distinctive words. So these older methods merely identified, counted, or weighed words, but they completely failed to capture true similarity.
Let's move to section 2, the breakthrough, mapping meaning with coordinates.
We finally reached a breakthrough where AI stopped counting and started treating meaning as a geometric space. And this brings us to the absolutely crucial core concept, the word embedding. So, what is it? An embedding is a dense numerical vector that represents a word's meaning by giving it specific coordinates in a continuous vector space. In simple terms, embeddings finally convert meaning into a list of numbers, so that similar words sit close together mathematically.
To really grasp this, we can relate embeddings to a few simple analogies. First, think of a meaning map. Just like cities have physical coordinates, words now have meaning coordinates. Or think about the student friend groups analogy. Imagine a new student joins your class. You don't know them at all, but you notice they're always hanging out with cricket players and team captains. You can safely guess they probably like sports. An embedding learns a word in the exact same way by looking at its neighboring words. This leads naturally to word neighborhoods and ingredient clusters, where related concepts just naturally group together in space.
And this brilliantly illustrates how these clusters actually work once they're mapped out. You've got the royal neighborhood, which groups king, queen, and palace. Right next to it, in a completely different mathematical location, is the medical neighborhood, with doctor, nurse, and hospital. And somewhere else entirely, a cricket cluster with batsman, bowler, and wicket. Words just naturally form these distinct clusters in the vector space based purely on how we use them.
Moving on to section 3, the mechanics, how models learn meaning.
So how exactly does the machine figure this out all on its own? Well, it all goes back to a very famous linguistic rule by John Rupert Firth. You shall know a word by the company it keeps. Basically, models learn by reading millions and millions of sentences across the internet, or vast libraries of books, just to see which words repeatedly hang out together in the same context.
One of the most famous models to pull this off is word-to-vec. Think of it like a student constantly taking fill-in-the-blank tests. This is its continuous bag of words method, or SIBO for short. The model gets an input, something like, the king wore a golden blank, and it has to predict that missing word, crown. By constantly practicing how to fill in those blanks, it learns which words share a semantic space.
But word2vec also has a second method called skipgram, which does the exact reverse. Here, you give it a single target word, like king, and the model has to predict the entire surrounding neighborhood of words like queen, palace, and throne. After millions of these predictions, similar words are mathematically forced closer together in that vector space.
Now, while word2vec is definitely famous, it's not the only way to build this map. Let's compare the classic big 3 embeddings. We know word2vec uses local word prediction. Then we have GLOVE, which stands for Global Vectors. GLOVE acts more like a giant relationship map for the whole library, learning from global word co-occurrence statistics across the entire text corpus. And finally, there's FastText, which breaks things down even further.
Now, what's really interesting about this is FastText's genius ability to look inside the words themselves. Instead of treating the word playing as one solid unbreakable block, it sees word pieces like pla, lay, and ing. This is incredibly helpful. It means if FastText sees a rare word, a weird misspelling, or a complex word in a morphologically rich language, it can use those subword character chunks to accurately guess its meaning.
Which brings us to section 4, the payoff, real-world AI applications.
We have these incredible mathematical maps now, but why does it actually matter? Because the moment machines could suddenly calculate meaning similarity, an entire industry was revolutionized. Word embeddings are the absolute foundation for sentiment analysis, semantic search, recommendation systems, document classification, chatbots, and machine translation. All of these powerful, everyday digital tools suddenly became possible.
To put that into perspective, let's think about a practical example, semantic search. Imagine you search a company's website for the word refund, but their policy document only ever says money back. An old-school keyword search engine would completely fail to find it. But because these phrases have similar meaning coordinates in our vector space, semantic search knows they match perfectly, even though the exact keywords are completely different. A real game changer.
But of course, no system is perfect. Section 5, the context revolution, fixing the flaw.
So, what could possibly go wrong with such an incredible system? The major flaw was polysemy, words that have multiple meanings. Imagine these two scenarios: depositing money in a financial bank versus sitting by the muddy riverbank. Classic embeddings like word2vec and glove gave the word bank only one static vector. They completely confused the two drastically different meanings, basically blending finance and mud into one useless average coordinate.
So the crucial point here is that this exact limitation forced the next great leap in NLP. Models like ELMo and BERT launched the context revolution. We moved away from static embeddings, which gave one fixed vector per word, and shifted to contextual embeddings, where the vectors actually change fluidly based on the entire sentence. Now the word bank gets a financial vector if it's near money, and a geographical vector if it's hanging out near the word river.
And that evolution right there set the stage for the massive AI models we interact with today. But it all started when we stopped simply counting words and started actually mapping them. As you walk away from this explainer today, if you remember just one concept to build your mental model of AI language processing, let it be this: word embeddings are meaning coordinates for words. But it leaves us with a pretty fascinating question. If machines can map meaning this well, what human concept will they map next? Thanks for tuning in, and keep exploring.